Hey, welcome. So this time I'm going to look at equilibrium solutions of the fluid equations. I'm going to look at cases where we're in steady state, so there's no time derivatives, so everything is not changing in time. And this will mean we have the forces on the system are balanced, so there's no imbalance, there's no net acceleration of the system. And we look at a few examples of this. So first will be hydrostatic equilibrium. So it's just a fluid like a gas in a column. Look at how the forces, so the gravity force downwards is balanced by the pressure force in the fluid. And then we look at a case of a flow through parallel plates, so where the pressure gradient is being balanced by the friction against the walls of the plates. And so we're going to use the fluid equations, most of the time essentially based on the Euler equations with additional terms coming from the collision operator in the kinetic equation. So there's going to be terms involved in the Navier-Stokes equations, but they're all going to be steady state. So that's what we mean by equilibrium. So it's steady state. So in the lab frame, partial d by dt is equal to 0. So there's no time derivatives in the system. And in many cases, there's not going to be any flow either. So static here means that there's no flow. So it's just sitting still, nothing's changing. It's the most simple case we can find really. So we're going to base this on Euler's equations with extra terms. And so start with the density equation. So d rho by dt plus u dot grad rho is minus rho times of u. So this is just the density equation. Then we have the momentum equation. So d u by dt plus u dot grad u. This is all in advection form. And then here we have the forces on the system. So because I'm going to add more terms, I'll basically put the density on this side. So we have the mass density here, and then here these are all the forces. So we have minus grad p, so the pressure force, and then we can have extra forces. So we can look at various cases where this is either friction or this is gravity, but there can be other forces. And in plasmas, of course, this could be the Lorentz force as well. So we have other electromagnetic forces, and then finally we have the pressure equation. Sorry, so dp by dt plus u dot grad p. We have a gamma ratio of specific heats, and then again divergence of u. So this is the equations we're going to consider. First, we're going to look at hydrostatic. And by static, what I mean is that u is equal to 0. So what you find here is that because d by dt's here are 0, so all these time derivatives are 0. The u is 0 here, so this equation entirely vanishes, as does the pressure equation. And this also goes to 0. So the only thing that's actually left is these two terms here. And the same thing happens in plasmas, where essentially everything disappears except for some terms in the momentum equation, which are just saying that force balance has to exist. So there has to be balance between the various forces on the system. And so in this case, what we're going to look at is a case where this pressure gradient is balanced by gravity. And so here we're going to consider a case where force is basically the mass density times gravity. And if we have a system like the Earth's atmosphere, where we have, so the ground is like this, that's the ground, we have height, which it's going to call y, and then we have pressure and density, so rho is just a function of y, and pressure is just a function of y, and I said u is equal to 0. And then we have a force balance here, and the force is just given by this. So I'm just going to call G. G is downwards, obviously, so G is minus scalar G, is 9.81 meters per second squared, times y. Okay, and this means that this entire thing just becomes basically dp by dy is equal to minus this. So this whole equation just becomes dp by dy, because p now only depends on y, and this whole thing is just minus this g times rho, which has come from g rho here. So this g just becomes g, this rho here, then we substitute this into this equation, and this is just a gradient and a vector in the y direction. So that is essentially it. So the pressure is decreasing, this is negative, so the pressure is decreasing as we go up, because we have essentially each layer, consider like a thin layer of fluid here. This is like dy. This width here is like dy. There's a weight. You can take this dy over here and say, consider like dy times rho. It's basically like the mass of this layer of fluid, and that is being supported. The weight of that fluid, so this is multiplied by g. This gives you the weight. Is supported by the pressure of the fluid below it. So the fluid below is pushing upwards and is balancing the weight of this fluid. And so as you go up through the atmosphere, the pressure is dropping. And now you can combine this with ideal gas laws to work out how the pressure and the density are actually changing in y. So you can integrate this, because here rho is also a function of y. So you want to be able to integrate this equation to work out what p is as a function of y. And so we can combine this with the ideal gas law. So PV is in kBt. And here we can just divide this through by this volume. So P is N over V kBt. And now this N is the number of particles per cubic meter. And so this number of particles per volume, so this is number of particles, so this thing is number of particles per volume. This we can relate to the mass density. So N over V is basically mass density divided by the average mass of each atom or each particle in the gas. Because if each particle weighs this much MA, then this is how much it weighs per volume. And so we can just substitute this into here. So we have that, so here we have P is equal to, now we have rho over MA kBt. And this is going to let us, substitute essentially this P into this term here. So substitute this rho into there. And so we end up with an equation which is dP by dy. We have a minus g, and then we rearrange this equation so we have an MA comes over here, MA, we divide through by kBt comes over here, and then we have rho equal to P. And now we have an equation for P on the left hand side, dP by dy, only depends on P and some constants, so the mass, the average mass of particles in the fluid, the gravity, and the temperature of the fluid. And so we can integrate this in, and so we integrate this all up, and we end up with a solution which is that P is P naught times an exponential e to the minus over here over a constant which is m g over kBt times y, which is the height. And now this tells us that the pressure decreases exponentially with height, assuming of course that T is in fact a constant. In reality, of course, temperature is changing, and so this scale length will change. But we can write this whole thing, this is essentially y divided by a length scale. So we have a length scale, which is just kBt over MAG. And this is around 8.5 kilometers for Earth's atmosphere. For Earth's atmosphere. So this is one way, just a simple example of an equilibrium system where we have a pressure gradient balancing an external force. So a slightly more complicated example is where we have a viscous flow. And in particular, we're going to look at a case where we have flow between two parallel plates. So we have two plates like this. And these are solid plates. And then we have flow down the middle. And we're going to assume that this is a very long this is a very long plate compared to its width. So it's going to have some width here, which is going to be called L. And it's a very long plate, so we can consider that the velocity is only in this direction, so we're going to call this the x direction here. This is x, and then this direction, vertical direction, again is the y direction. And so u is just some function of y. So u is the velocity is changing with y, but it's only in the x direction. So it's like this. So we have so a flow which is in the x direction, but which is changing with y. This will allow us to simplify some things. So this wouldn't be true, for example, at the entrance or exit of the plates. So where the parallel plates end, there'll be some flow in other directions. But if we're assuming we're looking near the middle of the plate, far away from the boundaries of the system, then the flow must be just parallel to the plates, providing we have laminar flow, of course, so there's no turbulence or anything. And again, we look at the steady state solution, but now, of course, we do have a flow. So in this case, we can look at the momentum equation and write this down. So we have du by dt, again, which is equal to 0. U dot grad u, and we have the terms on the right side. So we have, I'm going to write this density here. So we have again minus grad p. And now instead of the gravity, we're going to look at viscous forces. So we add the viscosity term to the momentum equation. So we have a mu dot squared u. Then we have this second term here, which is actually going to be 0 in this case, but we'll put it right in for completeness. And because we assume that the plate is very long and thin, and it's in steady state, here we're going to assume that the flow is incompressible. So the flow is just constantly moving through the fluid through the plates, and if we look at any one location, it's not any different from any other. So we assume that this compression term goes to 0, and so here we need to worry about this term a little bit here. So the velocity is not 0, so we can't just say that this is immediately 0. But what we can say is that if the flow is incompressible, and if the fluid is just moving along in this direction, what must happen is that whatever flows in this side must flow out the other side. And so if the density is constant because it's not compressed, then the flow velocity must be the same here as it is at the end. And so there's no gradient of the velocity, and so this is also equal to 0. And so all that we're balancing are these two terms. So we're balance the pressure gradient against the viscosity. Again, this simplifies as well because we can just u is only in the x direction, so we just take the x component of this, so the component along the plates, and u is only changing in y, and so this just becomes a second derivative in y. And so we can write this whole thing is just dp by dx, it just comes from here, must be equal to mu, and then here we have a second derivative dy squared of ux. So we have an equation for the second derivative of ux, so the flow in the x direction, which depends on this pressure. Now we can make some further arguments to simplify this. So one is that if you have a narrow plates, so the distance between these plates is not too large, then this pressure gradient must be essentially constant in y, The idea is that if there is any difference in pressure between points along y, then the fluid will very quickly accelerate and cancel out the pressure differences. And so pressure must be constant in y, and therefore dp by dx must also be constant in y. And so we have that the second derivative of ux, so d2 ux by dy squared is 1 over mu dp by dx. And this is all independent of y. And so this is just a simple quadratic. And so we write that the ux must be proportional to y squared. It must be like y squared plus something involving y. So it must be a quadratic. And we can look at what this must be by looking at the boundary conditions. So at the walls of the plates, the fluid is in contact with the wall, and so the fluid velocity goes to 0. So at the wall itself, we have no slip conditions, and here ux equals 0, and the same at the bottom here, so ux is equal to 0 on both these boundaries. And so ux equals 0 at so boundaries here, ux equals 0 at y equals 0 and y equals L. So ux is 0 at y equals 0 and y equals L. And this is the no slip condition. And so using these boundaries and the fact that this is a quadratic, we can very quickly write down what ux must be. So ux must be something which has a y at the beginning, because when y equals 0, this must go to 0. It must have an L minus y, or y minus L, because now when y equals to L, this must go to 0. And so this whole thing now satisfies the boundary conditions. And so we're left to work out the constants. And so the constants must be proportional to this, so we have a dp by dx and 1 over mu. And now if we have a quadratic, what we end up with is a factor of a half coming down here, so we must have basically a half here. So when you differentiate this twice, y squared will give us a factor of 2, and that will need to cancel out to go to here, so we have a factor of a half here. Okay, and then finally here we have a minus sign. So we have a minus y squared, so here we just need a minus sign to cancel this out. And so now this starts to make sense. So dp by dx is falling, so if dp by dx is less than 0, so the pressure is highest on the left hand side and low on the right side, then the flow is from high pressure to low pressure. So ux is greater than 0 inside the channel. So that must be correct. So then if this is negative inside the channel, this is positive because y is less than L, and so this whole thing becomes positive. And so we have a flow which looks like a quadratic, pinned to 0 at the boundaries, and is proportional to the to this dp by dx divided by mu. Okay, so in in this diagram, u has a quadratic form like this. So u is something like this. So it's like a quadratic pinned to 0 at the two boundaries, and proportional to the pressure drop, like this. Okay, so then what we could do is we could use this formula to try and work out what's happening with the pressure. So in the pressure equation, which I'll write down here again, so we have dp by dt. Apologies, this should be partial derivative here. Plus u dot grad p. That's again minus gamma p divergence of u. That's the full pressure equation. Now we've assumed at the beginning that this was equal to 0, But now we've just found that there's a pressure drop here, so dp by dx, which is proportional to ux. So if u dot grad p here is equal to ux dp by dx, because pressure is just varying in the x direction, u is also in the x direction. This here we're considering steady state, so that's equal to 0. And now u is positive and dp by dx is negative, and so this is less than 0. And now this is less than 0, but we assume that this is equal to 0. So does this mean that the divergence of u is bigger than 0? Because that's what would have to happen for this to work. No, this is showing that we have an inconsistency in our equations, and what we need is an extra term on this right side here, and we can find out what that term is by essentially balancing this pressure against the viscosity. So we said way back at the beginning up here that this dp by dx is driven by this viscosity, so dp by dx is just mu d2 u by dy squared. And so I'm going to write down what this is. So this is equal to ux, and now we have mu d2 ux by dy squared. So this term here on the left hand side has this form where we have essentially something that looks like the viscosity. This looks like the viscosity multiplied by ux. And so what we're missing here is an extra term which looks like mu. Then here we should have a u dot, and then here del squared u. And if we got this term, we must have the other term as well. So in general we'd have a mu over 3 u dot grad divergence of u. So these terms are coming from the viscous heating. So this is the change in pressure and the work being done by the fluid in order to drive. This is work done against viscosity. So when you're driving fluid through the system, you're doing work because you have a pressure and you have a velocity. So in order to drive fluid through the channel, you're doing work, and that work then goes into the viscous term and ultimately into the walls of the channel. So you're doing work in order to keep the flow going, and this is what this term represents. So it's the work done by the fluid against the viscosity, and that balances this term here, whilst maintaining. So this term is still equal to 0, and this term, so the divergence of u here is 0. And so in this system, this term here is balanced by this term here. And this shows the importance of being consistent when you add dissipation terms. So without this extra term, the pressure equation didn't balance and wasn't consistent with the other equations. Okay, thank you very much.